The main goal of this test is to compare different mountain bike brands' rigidity. Each brand and frame has different ride characteristics. Some feel soft and flexible, while others feel rigid and stiff. The frame's flex and stiffness plays a major role in how the bike feels underneath you while you're riding it. To measure this, we'll be applying forces to the bike frames in the vertical and horizontal directions, the same way they would be applied to the frame from a rider riding the bike. We will be collaborating with Frameworks, a new mountain bike company owned by Nico Malali, a professional mountain bike racer. Nico would like to see how his frames rank in stiffness compared to other mountain bike frames currently on the market. There is no data currently available to the public comparing different mountain bike brands' frame stiffness. The data we collect will help to develop a quantitative scale and compare different mountain bike brands' frames on the rigidity. The more or less rigid a bike is doesn't decide if it's better or worse. It is strictly a preference and will just be another available tool for people to choose a bike that better fits their riding style.
Moving to our fixture design, as you can see, here's an image of what we catted up for our final designed fixture. It is designed to hold the rear axle securely in a plate that allows us to adjust for different widths of rear axles. And then the front is secured by a slide, as well as some machined triple clamps, as well as aluminum rods, which replace the fork members to be able to create solid connections. Threaded bar will be used to apply force to the frame, both laterally and potentially horizontally. This design, we designed it in such that it can fit a wide range of bike frames. So that way we are not limited in the amount of frames that we can test. All components were modeled using SolidWorks. As all the team members, most of them are most familiar with SolidWorks, so we chose to use SolidWorks as our design software of choice. Next, we'll go to fixture fabrication. So all machine components are made of 7075 aluminum, while the welded components are steel. A mix of manual machining, lathe work, and CNC work was done to fabricate this fixture. And then the steel frame was TIG welded together, so tungsten inert gas welded. The machining was done in the Clarkson University machine shop, as well as within the Speed Lab.
Moving on to an overview of our testing method. Testing the frames involves creating a reaction to a force applied at the bottom bracket, either a horizontal force or a vertical force. All forces will be applied at the bottom bracket for consistency, and we'll get into the specific steps of horizontal and vertical loading on the next couple of slides. Horizontal loads will be applied via a screw, or if that doesn't produce enough force, we are also going to implement a L bracket to create forces in the horizontal direction, and vertical forces will be created by hanging weights through the bottom of the frame. Dial indicators will be zeroed before every test, and the change on the reading will be observed to determine the displacement of the frame due to loading. This displacement will then be used to calculate the stiffness of the frame. So the experiment method for horizontal loading is pretty simple. It involves stripping the bike down to a frame, getting rid of all components that might get in the way of the test, including brakes, drivetrain, and especially suspension. Mount the bike in the frame jig, adjusting the triple clamp to ensure that everything stays nice and tight, and making sure that the rear axle is aligned properly and that the spacing feet are extended to the maximum distance that they can be given the rear axle length. Zero out your dial indicators to get an accurate measurement. Apply a known force. In this case, for this procedure, it's 50 pounds, but the force is adjustable depending on what is necessary to observe displacement. Record the measurement on the dial indicator as a result of the applied force. Follow the steps you used to install the frame and reverse to remove it, and prep the next bike by the same steps to get ready for the next test.
The process for measuring deflection during vertical loading is very similar to that of horizontal loading, with the key difference being how the force is applied and where the measurement is taken. For vertical loading, the force will be applied by a mass hung from the bottom bracket. The measurement will be taken at the front edge of the sliding track. A dial indicator will be zeroed on the front edge of the sliding track prior to the mass being hung, and then its measurement will be recorded after the force is applied. After this, the bike will be reassembled and the next frame will be prepped for testing.
Testing consisted of checking the fit of all jig components with a specialized enduro in size S4. We hung an 11 kilogram weight off the bottom bracket of this and measured the horizontal displacement of the front track using calipers. For the 3 trials we conducted, we measured the deflection to be 0.05 millimeters, which means that the stiffness for the specialized enduro is found to be 215,820 newtons per meter.
Analysis for this test will consist of ranking each frame from least rigid to most rigid based off of our test results, and also comparing our test results to how each bike feels while it's actually being ridden.
Since we found that the load frame design is viable for this test, design will be revised over the summer to make changes to the steer tube, triple clamps, and load application to improve accuracy and usability for the future. We'll return in the fall to manufacture these parts, retest to verify that the changes improve the test, and then work with Nico Malali to test his frames and more frames from the industry as well.